Today we're going beyond right triangles. We're going to go ahead and take a look at non-right triangles, which are also known as oblique triangles. And what we're going to do is we're going to relate the sides and angles in an oblique triangle to calculate the area of a triangle. And so hopefully you recognize area equals half base times height. B is the base, h is the height. And you need to understand that we're dropping the height from one vertex to the opposite side and forming a right angle. And from there, we're going to go ahead and integrate what we know of trigonometry. So if you take a look at this triangle ABC, we're working with angle A as the first reference angle. And so what I'd like for you to think about is how can we relate the height drawn to base AC and relate it to theta using one of the sides of the triangle, ABC. And if you notice, AB is the only side of both the green triangle, that right triangle, and big triangle ABC. And so to relate those sides, we have the opposite side H and we have the hypotenuse AB. So that is sine of theta, or A, is our reference angle, and that's equal to opposite over hypotenuse, so H over AB. And if we solve for height, we get that height is AB times sine A. The other component to half base times height is understanding what the base is, and so looking at where the height is, it's drawn to base AC. So making sure we understand in this triangle ABC, the height we are expressing as AB times sine A, and then the base is going to be AC. So now we piece together and we substitute in. So if the base is AC, then I'm going to take the formula area equals half base times height, and I'm going to substitute in AC, and then I'm also going to substitute in this expression for height, so AB times sine A. The last piece then is reminiscing about and going back to what we call special labeling, where you can name sides of a triangle by the letter opposite side. And so angle C, for example, becomes lowercase c when you look at the side opposite it. Angle A is opposite lowercase a side, and then angle B is opposite lowercase side B. And if we look at the sides that we need, we have AC is going to be lowercase b, and we have that AB in this formula is going to be lowercase c. And so you'll notice below the triangle I've marked up, we have area equals, instead of AC we have B, instead of AB we have C, and then times sine of A. And so really understanding that we can calculate the area of a triangle if we are given two sides in the included angle. And this relationship will hold true. Let's go ahead and take a look at a different reference angle. If you're looking at the next page in your notes, we have angle C as the reference angle. We still want to relate the height drawn to base AC here to reference angle C using a side of triangle ABC, which in this case would be BC. So here we've related C, H, and BC using sine. Solving for H, we have sine C times BC. The base is AC, and so substituting in for H, we have sine C times BC, which is also on the right-hand side of the sheet, and then times the base, which is AC, so B is AC. And then through some reversing of multiplication using the commutative property of multiplication, it can be written in that way, and then using the substitution of letters opposite the corresponding sides, you get half of AB times sine of angle C, which again are the two sides in the included angle. The special case comes when you want to look at that last angle, angle B. If you notice, to drop the height to side AB, you have to extend side AB. And so really what you look at in order to create that ratio for sine is not angle B inside the triangle, but the supplement of angle B, which is 180 minus the measure of angle B. And from there you can relate the opposite side height to the hypotenuse of that triangle that has that reference of angle 180 minus measure angle B. If you notice the setup that we used on the other two triangles, we have sine of 180 minus measure of angle B becomes sine of B. And so herein lies the question of why can you say that 180 minus the measure of angle B is the same thing as the measure of angle B. And for that, you're going to take a look at this concrete example here. So let's say I have a fixed segment, which we're going to use as the hypotenuse, and I want you to rotate that segment on a coordinate plane 68 degrees. From our previous work, you should understand that 68 degrees is a counterclockwise rotation. And if I wanted to create a right triangle from that rotation, I would drop down the opposite side to the horizontal axis in form of that right triangle. And so the sine of 68, that angle, is going to be the opposite side you drop down over the hypotenuse. Now taking a look at the supplement of 68, since we're saying that the sine of 180 minus the measure of angle B can be substituted with just the measure of angle B. So 112 from the horizontal, positive movement counterclockwise. If you notice, when we use that segment, the hypotenuse, and we drop down that opposite side, we create a 68-degree triangle still. The opposite side is still the same length, the hypotenuse is still the same length, so these generic abstract ratios of opposite over hypotenuse are going to remain the same. Go ahead and take a look at the example on the next page. Looking again at another concrete example, we have that 20 degrees counterclockwise would rotate in that way. Sine of 20 degrees would be the opposite length that would be drawn down, given the hypotenuse was what was rotated to begin with. And now looking at its supplement, which is 160 degrees, you'll notice that when we go that 160 degrees with that fixed segment, the hypotenuse, dropping down that opposite, we still get that same triangle where we have a 20-degree angle. And so the triangle that's generated from a 160-degree angle is still going to get us the same ratio for sine. If you notice, the thing that does change when we do this rotation from an angle to its supplement, on the left-hand triangle, we have that horizontal length is positive to begin, it's in the positive x's, versus this horizontal length, which is negative in the right-hand triangle. That is an adjacent side to the reference angle, which is not necessary to work with what we're doing in the area formula, but understanding that we can ultimately say sine of an angle is equal to sine of its supplement is the big takeaway here for now. And so if you look at the bottom of this page, we have some nice summary here of the relationship of two sides in a triangle times the sine of its included angle divided by 2 equals the area of a triangle. At the top of this last page of notes, you see some examples worked out for you. So in each of these, you see two sides are given, and then if you notice, the included angle is given in each of the diagrams. What I at least expect to see from you is a setup, a plug-in of the two sides, times the sine of the included angle divided by 2, and then your answer with labels. You do not have to set up this generic formula. If you'd like to be walked through a couple of examples and then now you try some, go ahead and keep watching this. Otherwise, I want you to pause. I want you to try them on your own, compare them to the key that's at the bottom, and then either way, whether you watch the video or you do them on your own, show me your completed work to then get the independent practice assignment. It's a 2-page assignment to keep practicing this idea of area using two sides in an included angle versus the traditional half base times height. So for this first example, if you'd like to see me talk through it, it's going to be pretty quick. We have two sides. We have an included angle. This is angle A. We have side lowercase b and side lowercase c. So if I'm going to really go over the top with my setup, I'd have area equals 1/2 b and c times the sine of included angle A. Area then equals 1/2. And I have the side B technically is 18 times 11. It really doesn't matter the order that you multiply, you'll get the same product, times the sine of 70. And then from here you would calculate using your calculator. I'm going to go ahead and cheat and look at the answers at the bottom. I don't have my calculator on me, so you get 93 3/100. And then don't forget that label. We are looking at square units here for area of 93.03 square centimeters. Looking at the next one, we have... Again, if I want to be over the top, lowercase side a, lowercase side c with included angle b. And so I could say 1/2 of a times c times the sine of angle b equals area, or at a minimum, show the substitution. So I have 16 times 15 times the sine of 95 degrees. And if you were to plug that into your calculator onto the nearest hundredth, again, you would get 119 54/100 square centimeters. And to look at the last one here, I'm just going to set up what I expect to see. So we have two sides in the included angle. I can do 1/2 of 8 times 11 times the sine of 35 degrees. And again, using your handy-dandy calculator and rounding to the nearest hundredth, it does look like you got 25 24/100 square centimeters. With that, go ahead and check in with me, please, so I can give you the additional practice.